Ever stop and wonder how your phone just like instantly pulls up a photo that's stored on a server maybe thousands of miles away?
Or how these huge online services manage, unbelievable amounts of data for literally billions of people.
Exactly. And it all seems so seamless, right? But underneath, there's some serious engineering going on.
There really is.
Today, we're taking a deep dive into that hidden world, networks and distributed systems. We'll be unpacking the core ideas, the cutting-edge designs, basically everything from Chapter 19 of Operating System Concepts, the 10th edition by Silberschatz, Galvin, and Gagne.
It's a foundational chapter.
Our goal here is to give you a clear, kind of engaging shortcut to understanding these systems.
So you can really appreciate the complexity behind all the digital stuff we do every day.
Right. So let's start at the beginning. When we say distributed system, what does that actually mean? What's the defining feature?
Well, the fundamental definition is a collection of processors that do not share memory or a clock. That's the key.
No shared memory or clock.
Right. Instead, each processor, or we call it a node, it has its own local memory. And they communicate, obviously, over a network. Think of them as loosely coupled nodes.
Loosely coupled, okay.
Yeah, an analogy might be like a team of specialists working on a project. Each has their own desk, their own tools, but they're constantly talking, sharing results to get the job done together.
That makes sense. So they're independent but cooperating. What are the big advantages then? Why build systems this way instead of just, one giant computer?
Oh, there's some major reasons. 3 big ones, really. First is resource sharing.
Okay.
So users at one location can use resources, maybe a specialized database, maybe some heavy-duty hardware like a supercomputer or GPU, or even just a fancy printer located somewhere else centrally. It's efficient.
Right, you don't need a supercomputer on every desk.
Exactly. Second, computation speedup. You can take a huge task, break it into pieces, and run those pieces at the same time across lots of different machines.
Ah, parallel processing.
Precisely. Crucial for big data stuff. And related to that is load balancing. If one machine gets too busy, you can just shift tasks over to ones that are less loaded.
Keeps things running smoothly.
And the third big advantage is reliability. If one part of the system fails, say a server crashes, the rest of the system can often just keep going. As long as you've built in enough redundancy, backup hardware copies of data, the whole thing doesn't grind to a halt.
So redundancy is key for reliability.
Yeah.
Makes sense. Okay, so if you're building one, how are they typically set up? What are the common structures?
You mostly see 2 main configurations. The most common is probably the client-server model.
Like browsing the web.
Exactly. Your computer is the client requesting a web page from a web server. The server has the resource, the client wants to use it. Pretty clear roles.
Okay.
Then there's the peer-to-peer model. Here, things are different. There's no central server. All the nodes are kind of equal.
So anyone can be a client or server.
Right. They can act as both. Think about some older file-sharing networks or certain online games where players connect directly. Everyone shares the load.
Interesting. So different ways to structure them.
And to really understand how any of these work, you absolutely need to get the networks connecting them. They're the highways, the infrastructure.
Right, the network.
Yeah.
We hear terms like LAN and WAN all the time. What's the actual difference in simple terms?
It mostly boils down to geography, and that affects speed and errors. Local area networks, or LANs, cover small areas.
Like an office building or home Wi-Fi.
Exactly. A single building, maybe a campus, they tend to be very fast with very low error rates.
Yeah.
Ethernet cables, Wi-Fi, those are classic LAN technologies.
Gotcha. And WANs?
Wide area networks, or WANs, they span much larger areas. Cities, states, countries, even the globe.
The internet itself is a WAN then?
Well, it is a massive collection of interconnected WANs and LANs, yeah. WANs use all sorts of links, fiber optic cables, satellite, microwave. Routers are key here, directing traffic across these large distances.
And they're generally slower than LANs.
Generally, yes, the average connection might be. But the backbone connections, the main arteries of the internet, connecting major data centers, those can be incredibly fast fiber optic lines. Think 40, 100 gigabits per second, or even more.
Yeah.
And, it's often a mix. Your cell phone data connection, your phone talking to the towers, sort of LAN-like, but the towers connecting to each other across the country, that's pure WAN.
That's a great example. Okay, so we have these different networks, different devices. How do they actually talk? How does my laptop understand a server halfway across the world?
Ah, that's the magic of communication protocols. They're the agreed-upon rules, the common language that lets all these different systems communicate.
A shared language.
Exactly.
Yeah.
And designing these protocols is complex, so it's usually broken down into layers. Think of it like a stack. Each layer handles a specific part of the communication.
Okay, layers. I remember the OSI model from classes, though I hear it's more theoretical now.
It is, but it's still a really useful way to think about the layers. The Open Systems interconnection model has 7.
7 layers.
At the bottom, layer 1, the physical layer. That's the actual hardware, the wires, the electrical signals, the raw bits, ASIOs and ones.
The physics of it.
Right. Layer 2, data link, handles sending data frames between directly connected devices, like across an Ethernet cable. It deals with physical addresses and basic error checking.
Okay.
Layer 3, network layer. This is where routing happens across different networks. It uses logical addresses, like IP addresses, and breaks messages into packets. Routers operate here, getting data from host A to host B, potentially far away.
The big picture routing.
Yep. Then layer 4, transport layer. This is crucial. It ensures reliable data transfer between applications on those hosts, making sure packets arrive in order, managing flow control. Think TCP and UDP here.
We'll come back to those, I bet.
Yeah, definitely. Then the top 3 layers, session, presentation, application, are closer to the user. Session manages the communication dialogue. Presentation handles data formatting like encryption or character encoding. And application is what users interact with: web browsers, email clients, file transfer programs.
So data goes down the stack, gets wrapped up, sent, and then unwrapped on the other side.
Precisely. Each layer has its own header information on the way down and strips it off on the way up. It keeps things modular.
But you said OSI is theoretical. What do we actually use?
We primarily use the TCP/IP model, sometimes called the Internet Protocol Suite. It's more practical, fewer layers, and it's what the Internet is built on.
Fewer layers. How does it map?
It sort of combines some OSI layers. Its application layer bundles protocols like HTTP web, FTP files, SSH, secure login, DNS naming, SMTP, email. The transport layer is still key, mainly with TCP and UDP. And the internet layer uses IP for routing packets. Below that is a link layer, similar to OSI's data link and physical.
So TCP and UDP are transport layer protocols in this model too.
Yes. TCP gives you reliable, ordered delivery, slower, but dependable. UDP is faster, connectionless, but unreliable, best effort delivery.
And IP handles the addressing and routing between networks.
Exactly. And a quick note on security. It's vital, obviously, but historically it was sometimes added later. That's why things like VPNs, virtual private networks, became important for creating secure tunnels over potentially insecure networks.
Okay, that makes sense. So we have layers, protocols, but how does my computer actually know who to talk to? How does google.com become an IP address? That seems like magic.
Not magic, but definitely clever. That's naming and name resolution. We need to translate those human-friendly names into the numerical IP addresses machines understand.
And that's DNS.
That's the domain name system. DNS. It's essentially a massive, distributed, hierarchical database. When you type a web address, your computer first asks its local DNS server. If that server doesn't know, it asks a higher-level server, maybe for the .com domain. That server points it down the chain, maybe to google.com servers, until eventually the specific IP address is found and sent back.
So it's a multi-step lookup.
It can be. But to speed things up immensely, results are cached. Your computer caches recent lookups, your local DNS server caches them, so you don't have to go through the whole process every single time. Way better than the old days of everyone needing the same giant text file of names and addresses.
Definitely sounds better. Okay, so DNS gets us the IP address. What about on my local network, like my Wi-Fi at home? How does my computer find my printer's specific hardware address?
Good question. That's typically handled by the Address Resolution Protocol, or ARP, at least on Ethernet-style networks.
ARP, okay.
Once your computer has the printer's local IP address, maybe from DNS, maybe static, it needs the physical NB address to actually send the data frame over the wire or Wi-Fi. So it shouts out via broadcast packet on the local network, hey, who has this IP address?
Like calling out in a room.
Exactly. And only the device with that IP address answers back, saying, that's me. Here's my MSE address.
Yeah.
Your computer then caches that IP to MAC mapping for a while, so it doesn't have to ask again immediately.
Clever.
Yeah.
Okay, so we know who we're talking to, IP via DNS, MAC via ARP. Now, how do we make sure the message actually gets there reliably? Networks aren't perfect, right? Packets get lost.
Yeah, absolutely do. And that's the critical job of the transport protocols, primarily UDP and TCP. But first, one more piece. Port numbers.
Port numbers.
Yeah. An IP address gets the packet to the right computer, but a port number tells the computer which application should receive it. Web servers usually listen on port 80, Secure web on 443, email uses others. It's like an apartment number for the application on that computer.
Ah, okay. So IP is the street address, port is the apartment number.
Great analogy. Now, UDP versus TCP.
Yeah.
UDP, User Datagram Protocol, is the fast, simple one. It's connectionless and unreliable.
The postcard analogy.
Exactly. You just send the packet, datagram, and hope for the best. No setup, no confirmation it arrived, no guarantee packets arrive in order. If one gets dropped by a busy router, too bad. The application has to handle it or just ignore the missing data.
Why use it then?
Speed. Great for things like streaming video or audio, online gaming, DNS lookups. Places where losing a tiny bit of data isn't catastrophic, and speed is more important than perfect reliability.
Okay, makes sense. So TCP must be the reliable one.
PCP, Transmission Control Protocol, is the workhorse for reliability. It's connection-oriented. Before sending data, it establishes a connection using a three-way handshake.
Handshake.
Yeah, basically SYN, SYN, ACK, ACK. A quick back and forth to make sure both sides are ready and agree on starting sequence numbers.
Sequence numbers?
Yes. Every chunk of data sent gets a sequence number. The receiver uses these to put data back in the correct order, even if packets arrive jumbled, and to detect missing packets.
And how does it know if a packet was received?
The receiver sends back acknowledgments, or ACKs. If the sender doesn't get an ACK for a piece of data within a certain time, it assumes it was lost and retransmits it.
Ah, so ACKs and retransmissions handle reliability.
Precisely. TCP also handles flow control, making sure the sender doesn't overwhelm the receiver, and congestion control, slowing down if the network itself seems overloaded. It provides a reliable, in-order byte stream.
But it's slower than UDP because of all this overhead.
Generally, yes. The handshake, the ACKs, managing state, it takes more effort. So it's a trade-off. Speed versus reliability. Use UDP when speed matters most and you can handle loss. Use TCP when you need guaranteed order delivery, like for file transfers or web pages.
Okay, that distinction is much clearer now. So with all this networking power, how do operating systems actually use it? How do they integrate these remote resources?
Good question. We generally see two main approaches or types of network-aware OCs, network operating systems, NOS, and distributed operating systems.
NOS and DOS, okay.
A network operating system, or NS, is what most of us use every day. Think Windows, Mac OS, Linux, even Android and iOS. They provide tools for you to explicitly access remote resources. The key word is explicitly.
Meaning I know I'm connecting to something remote.
Exactly. Like using remote login with SSH. You type server name and you're logged into another machine. You probably see different command prompt. Maybe you had to use different commands. You are aware it's remote.
Right. Or using FTP.
Perfect example. Remote file transfer with FTP or SFTP. Each machine has its own file system. Use specific commands like get or put to copy files back and forth. You're consciously moving data between locations.
Even cloud storage like Dropbox or Google Drive.
Yeah, arguably. While the interfaces are much friendlier, you're still interacting with a specific service to sync or access files that you know are stored in the cloud, which is just someone else's servers. The user has to adapt to the remote nature.
So the user is aware of the network in NS. How is a DOS different?
A distributed operating system, or DOS, aims for transparency. The goal is to make the network invisible. Users access remote resources in the exact same way they access local ones.
Seamlessly?
Ideally, yes. The DOS handles the complexity behind the scenes. This often involves different kinds of migration.
Migration, like moving things around.
Exactly. Data migration, for instance. Maybe a file you need is on a remote server. The DOS might automatically copy the whole file over, or maybe just the parts you need right now, kind of like demand paging for network files.
More efficient than moving the whole thing sometimes.
Definitely. Then there's computation migration. Instead of moving huge amounts of data to your computation, you move the computation to the data.
How does that work?
Imagine a massive database on a powerful server. You want to run a query. Instead of pulling terabytes of data to your machine, you send the query to the server, let it process the query using its local access to the data, and it just sends back the small result set.
Much less network traffic.
Way less. Remote procedure calls, RPCs, are a common technique for this. It lets a program on one machine call a function or procedure on another machine as if it were local.
Okay. And you mentioned migration. Any other types?
The third type is process migration. This is where an entire running program, or parts of it, can be moved from one machine to execute on another.
Why would you do that?
Several reasons. Load balancing, spreading work across machines, computation speed up, maybe moving the process to a machine with a faster CPU or a special GPU. hardware preference, needing specific hardware only available elsewhere, or data access, moving the process closer to the data it needs, combining computation and data migration ideas.
So DOS tries to hide the network using these migration techniques.
Right, making the collection of machines feel like one single, powerful system.
It strikes me that the World Wide Web kind of uses all of these ideas, doesn't it?
That's a great point. When you load a web page, data, HTML images, migrates to your browser. When you submit a form, computation happens on the server. And with things like JavaScript or WebAssembly, code migrates from the server and runs like a mini process right inside your browser.
It really is a giant distributed system.
Absolutely. But building these systems, especially aiming for that DOS-like transparency, is really hard. There are some major design challenges.
Okay, let's talk about those. What are the big hurdles?
I'd say 3 key issues are robustness, transparency, and scalability.
All right. Let's start with robustness. What does that mean here?
Robustness is about handling failures gracefully. In a distributed system, lots of things can fail. Network links can break, individual machines, hosts can crash, entire sites can go offline, messages can just get lost.
So the system needs to survive these things.
Exactly. It needs to detect failures, reconfigure itself to work around them, and recover when things come back online.
Yeah.
We often talk about fault tolerance, the ability to keep working, maybe slower, or with fewer features, even when faults occur.
How do you even detect failures if there's no central control?
It's tricky. A common method is using heartbeat messages. Sites periodically send out I am up signals. If a site stops hearing another's heartbeat, it might suspect a failure. It could then send an are you up message. But it's hard to distinguish between the site actually being down, the network link to that site being down, or maybe just the message getting lost. There's inherent uncertainty.
Okay, so once you think something failed, what happens?
Reconfiguration. Systems update their routing tables to avoid broken links. They might notify all other active sites that a particular site is presumed dead. If a coordinator process fails, they might need to elect a new one.
That sounds complex.
It is, especially if the network itself splits into partitions. You could end up with 2 parts of the system acting independently and maybe making conflicting decisions.
Oof. And recovery.
When a failed link or site comes back online, it needs to be smoothly reintegrated. It has to update its local information routing table state data by talking to the currently active sites.
So robustness is about handling failures at multiple levels. What about transparency?
Transparency is all about hiding the distributed nature from the user. Ideally, the user shouldn't even know or need to care that they're interacting with multiple machines across a network.
Like the DOS ideal we talked about.
Exactly. Accessing a remote file should feel exactly the same as accessing a local file. The interface shouldn't betray the location.
What are the benefits of that?
It simplifies things immensely for the user. It also enables things like user mobility. Imagine logging into any computer on the network, and your personal environment, your desktop, your files, your settings just follows you seamlessly. Things like centralized authentication, LDAP, and desktop virtualization help achieve this.
Right. So transparency hides complexity, and the third one was scalability. That word gets thrown around a lot.
It does. Scalability in this context means the system's ability to handle growth, more users, more data, more requests, gracefully. Meaning performance doesn't fall off a cliff as load increases. It might degrade slowly. Or you can add more resources, servers, storage, and performance increases proportionally, or at least close to it.
What makes scalability hard?
Well, just throwing more hardware at the problem doesn't always work. Adding more servers might overload the network or create bottlenecks elsewhere. Sometimes the fundamental design needs to change to scale effectively, which can be expensive.
So how do you design for it?
Often involves distributing not just the data, but also the control, avoiding central bottlenecks. And it ties back to robustness. Having spare resources for fault tolerance also helps handle peak loads. Efficient storage is also key.
Like what?
Techniques like compression making files smaller and deduplication.
Deduplication?
Yeah, finding and removing redundant data. If 10 users store the exact same operating system image, you only store one physical copy and just point everyone to it. Saves enormous amounts of space, which helps scalability. This can happen at the file level or even at the block level within files.
Clever ways to manage massive data. Okay. Robustness, transparency, scalability, big challenges. How do these play out in something specific, like, say, file systems?
Distributed file systems, DFS, are a perfect case study. A DFS is simply a file system where the clients accessing files the servers storing them, and the storage itself are all spread across a network.
And the goal is usually transparency, right? Make it look like one big local disk.
And that's often the ideal, yes.
Yeah.
To make network storage look and behave like local storage as much as possible.
So how are these DFSs typically built? What are the main architectures?
There are two dominant models you see. The first is the classic client-server DFS model. Think systems like NFS or OpenNFS.
NFS Network File System. I've heard of that.
Right, originally from Sun Microsystems. In this model, you have clients connecting to one or more dedicated servers. The servers manage the actual file storage and metadata, handle permissions, authentication, etc.
So the server holds the files.
Correct.
Yeah.
NFS specifically was designed for simplicity and fast crash recovery. It uses a stateless server protocol, meaning the server doesn't keep track of which clients have which files open. Each request from the client has to contain all the information needed to perform the operation. This makes recovery easy if a server crashes and restarts over. It doesn't have to rebuild any complex state about clients, but it can lead to more network traffic.
Okay. And OpenFS.
OpenFS, developed at Carnegie Mellon, took a different approach, focusing heavily on scalability. It minimizes server interactions by caching entire files on the client's local disk.
Caching the whole file.
Often, yes, or large chunks. You download the file when you open it, work on the local copy, and then upload the changes only when you close it. Much less back and forth with the server for reads and writes.
So different philosophies there. How do they actually appear to the user?
Typically, both NFS and OpenFS allow you to mount or attach remote directories into your local file system tree. So shared projects on your machine might actually live on a server somewhere else, but it looks like a local directory.
But the server is still a potential bottleneck or point of failure, right?
Absolutely. If that central file server goes down, everyone loses access. Clustering servers can help, but it's a fundamental aspect of the client-server model.
Okay, so what's the other model?
The other major one is the cluster-based DFS model, designed for massive scale. Think Google File System, GFS, or the open-source Hadoop Distributed File System, HDFS.
Used for big data, cloud stuff?
Exactly. The architecture is different. You still have clients, but they talk to a central metadata server, sometimes called a master or name node, primarily just to find out where file data is.
Just the metadata. Where's the actual data?
The actual file data is broken into large chunks, like 64 MB or 128 MB blocks, and stored across many different data servers or data nodes. Crucially, these chunks are replicated, stored on multiple data servers for fault tolerance and performance.
Replicate. Okay, so how does access work?
The client asks the metadata server, I need file X, chunks 1, 2, and 3. The metadata server replies, okay, you can get chunk 1 from data server A or B, chunk 2 from C or D, and so on. The client then connects directly to the chosen data servers to read or write the data chunks, often in parallel.
Ah, so the metadata server isn't handling the actual data transfer.
Right. It offloads that heavy lifting to the data servers. This avoids the metadata server becoming a bottleneck and allows for huge aggregate bandwidth by reading, writing from many data servers simultaneously.
That sounds much more scalable.
It is. GFS, for instance, was designed based on observations like hardware failures are normal, files are huge, reads are common, writes are often appends, and redesigning the API gives flexibility. This model is the foundation for tools like MapReduce, which process massive data sets in parallel across the cluster.
MapReduce runs on top of HDFS or GFS.
Yes, it's a programming model and software framework that leverages the underlying distributed file system to manage large-scale computations.
Okay, two different models, client-server and cluster-based. How do they handle naming and that transparency goal, making things look local?
Naming is critical in DFS. You need to map the user's name for a file, like homeuserdoc.txt, not just to disk locks, but potentially hiding which server holds it, or that it's split into chunks across many servers, or that there are multiple copies.
So hiding the location.
Exactly. That's location transparency. The name itself doesn't tell you the physical location. An even stronger property is location independence.
Independence.
It means the file's name doesn't have to change, even if its physical storage location does change. Maybe the admins move data between servers for load balancing. With location independence, the name stays the same. The system just updates its internal mapping. Systems like OpenNFS, HDFS, Amazon S3 support this.
That seems much more flexible.
It is. It gives better abstraction, allows admins to manage storage dynamically without breaking user paths. It decouples the logical name from the physical structure.
You mentioned diskless clients earlier. How does naming work for them?
Diskless clients rely entirely on servers for everything, even booting the OS. They use special network boot protocols like PXE to find a server, download the kernel, and then mount their entire root file system via DFS, usually NFS. Naming is crucial there. Their whole world is remote.
So how are these transparent names actually implemented? Different schemes?
Yeah, there are various naming schemes. The simplest is just embedding the host name, like server.path file. That's not transparent at all.
Right, you see the server name.
NFS uses the mount approach, attaching remote directories into the local namespace. So users might be local, but projects might be mounted from fileserver.data projects. This creates a somewhat coherent tree, but it can be complex to manage, and different parts become unavailable if different servers fail.
A bit patchy sometimes.
Can be. The ideal, often aimed for by systems like OpenAFS, is total integration, a single global name structure spanning all files across all servers, making it look just like one giant local file system. This usually involves mapping names to location-independent file identifiers internally, which can then be replicated and cached more freely. Okay, so we've found the file using its name. How does the data actually move? What's the mechanism for accessing remote file contents? The most basic way is the remote service mechanism. Your client sends a request, read block 5 of file X to the server. The server does the disk I/O and sends the data back. Simple, but potentially slow, like doing a network round trip for every single block read.
Sounds like NFS's stateless approach might do that a lot.
It can, yes, which is why caching is absolutely essential in DFS.
Caching on the client side.
Yes. Bring a copy of the data from the server to the client's local cache, memory, or disk, and satisfy reads from there whenever possible. It's like network virtual memory.
Reduces network traffic and server load.
Dramatically. Reduces latency for the user, too. Now, you have choices about what to cache: individual blocks, or larger chunks, or whole files like OpenAFS tends to do.
Pros and cons.
Caching larger units increases the chance the data you need next is already there, good hit ratio. But if it's not, the penalty for fetching that large unit is higher, miss penalty. It also makes consistency harder.
And where do you cache? Memory or disk?
Another trade-off. Caching on the client's local disk is reliable. The cache data survives if the client machine reboots. OpenFSS does this. Caching in main memory is much faster, enables diskless clients, and memory is getting cheaper. NFS primarily uses memory caching.
So caching helps reads. What about writes? When does modified data get back to the server?
That's the cache update policy, and it's critical. Option 1 is write through.
Write immediately.
Yep. As soon as the client modifies data in its cache, it sends a change straight to the server and waits for confirmation. Very reliable, little data lost if the client crashes. Very slow for write-heavy workloads, because you're waiting for the network and server disk I/O on every write.
So what's the alternative?
Delayed write or write-back caching. Modifications are written only to the client's local cache initially. The cache is marked dirty. Later, these changes are flushed back to the server.
When is later?
Various strategies. Maybe when the cache block is needed for something else. Maybe periodically. NFS flushes data blocks every 30 seconds or so. Or a popular one, write on close.
Flush when the file is closed.
Exactly. OpenFS uses this. You make all your changes locally, and only when you close the file are all the modified blocks sent back to the server. Great performance for writes, especially if you modify the same block multiple times.
But less reliable. What if the client crashes before closing the file?
That's the risk. Those unwritten changes are lost. So it's another performance versus reliability trade-off.
Okay, caching seems essential but complicated, especially consistency. If multiple clients cache the same file and one changes it, how do the others find out?
The million-dollar question. Cache consistency is maybe the hardest problem in DFS. How do you ensure clients aren't using stale, outdated cache data?
You.
Two main approaches. Client-initiated. The client periodically checks with the server asking, is my cached copy of file X still valid? This could be every few seconds or only when the file is opened. Simple, but can cause network traffic.
In the other way.
Server-initiated. The server keeps track of which clients are caching which files. If one client opens a file for writing, the server can proactively tell all other clients caching that file, hey, invalidate your cache for file X, or even stop caching file X for now, you have to go through me.
That sounds more efficient maybe, but more complex for the server.
It is. The server needs to maintain state about client caches. Cluster-based systems like HDFS often simplify this by having rules like only one writer at a time or focusing on append-only writes, which makes consistency easier than systems like GFS that need to handle concurrent random writes.
Wow. Okay, so from the basics of networks not sharing memory, through layers, protocols, naming, OS types, design challenges, and finally DFS architectures and caching. That was a lot.
It really covers a huge amount of ground, doesn't it? From the fundamental concepts to the nitty-gritty details of how files actually get moved around reliably and efficiently.
It's clear why this is such a complex field. So much engineering has to happen just right.
And what's really interesting is how it keeps evolving. The lines blur between client-server and cluster systems. People are even finding ways to layer older systems like NFS on top of newer ones like HDFS for compatibility. It's constant innovation driven by those core challenges: performance, reliability, consistency, scale.
So wrapping this up, what's the big takeaway for someone listening? Why should they care about distributed systems?
Well, the takeaway is that you use these systems constantly, every single day. Streaming video, cloud storage, web searching, online banking, social media. It's all built on these principles of networks and distributed systems.
Right. It's not just academic, it's the foundation of our digital lives.
Exactly. Understanding even the basics why caching matters. The difference between TCP and UDP, the challenge of consistency helps you appreciate the incredible engineering involved. And honestly, it can make you a better user, a better developer, a better problem solver in this connected world.
It really pulls back the curtain on how so much of modern technology actually works. We hope this deep dive gave you a much clearer picture of these remarkable, essential systems.
Keep exploring, keep learning. There's always more to discover.
Absolutely. Thanks so much for joining us for this deep dive into networks and distributed systems.